Okay, we're going to try recording and see if we can actually reach the cloud. Today, we're going to do a second acoustic phonetics lecture. And in this lecture, we're going to talk about the acoustics of consonants, what they look like on waveforms and spectrograms. We'll talk a little bit about how they interact with the acoustics of vowels. We'll talk about spectrograms in general and how you go about reading spectrograms, using the knowledge you have from vowel acoustics and consonant acoustics. And this will lead into a question of how a computer reads a spectrogram. Because as we'll see, that in speech technologies today, basically feed SR systems, automatic speech recognition systems, spectrograms, not visually, but in terms of a matrix of numbers or tensor in some cases, but basically a big two-dimensional matrix of numbers. So let's get started and talk about our goals for today in more detail. The big overarching theme is that vowels and consonants are acoustically diverse, and that consonants are much more diverse acoustically than vowels. So vowels, if you think about them, are mostly all the same. So your vocal tract is pretty open, sometimes more open than others, but it's always pretty open. You're not doing anything fancy or special with your tongue for the most part, other than having it relatively high or relatively low. Maybe your lips are rounded a little bit, but there's not a lot of action there. Your vocal folds are vibrating, unless you're Japanese, in which case your vocal folds may not be vibrating sometimes in certain contexts, but in general, this is the case. So vowels, they're sort of all the same. Now, consonants are different. You're doing all sorts of different gestures and manipulations of your vocal tract to produce a consonant. Different kinds of closures, constrictions. And sometimes multiple closures and constrictions. So when you're looking at the acoustics, as a result of the articulatory diversity, there's also acoustic diversity. And we'll see some of that today. Not enough to make you an expert in consonant acoustics, but enough for you to appreciate what is going on in this domain. So here are our objectives for today. So you should be able to distinguish vowels and consonants from one another, given a waveform and a spectrogram. This is something some of you have already become experts at as you've gone about doing your first homework and annotating vowels versus consonants. Yeah, you'll be able to identify the manner of articulation, roughly speaking, of different consonants, just given the waveform and the spectrogram. Yes. I would like to, I just don't know how. But I want to project from my iPad so that I can write on the slides. If anybody knows how to do that, then I would give them 5 bonus points, maybe 10. Any ideas how one might do that? I've tried that, but it a little bit and do command option 8. Let's try that. Command option 8. Accessibility That doesn't seem to be, doesn't seem to have those bindings. So, okay, let's try this. We will try stopping the share and see if this, I couldn't get this to work before. It kept like complaining to me. But let's try this. Well, it also bothers me. So let's see. No audio. Oh, this might work. Screen. Okay. That doesn't seem to be working. What do I tell it? What magic incantation do I use?
Go to the accessibility settings in system preferences. There's a checkbox which enables the screen.
Okay, let me try this really quick and see. Okay, maybe. Okay, does that work? Okay. So you need to know how articulatory events map onto acoustic events. And as part of that, you need to know the following terms, which are acoustic and articulatory in some sense. So closure, release burst, voicing, voice onset time, turbulence, aperiodic noise, anti-resonance and antiformant, MEL, a unit of pitch, MFCC, MEL frequency Kepstrel coefficient, and an acoustic model. So you should know what these things are. You should also know, and there's not a slide on this, but I'm going to talk about it, how tone is realized acoustically, and that's primarily as pitch. And you should know something about how phonetic knowledge can be applied to speech technologies research and development, because it can. So let's talk about consonants. So here is a nice consonant. What consonant could this be? Does anybody know? So here's something that kind of gives it away. It's a plosive. What is a plosive for review? Yes.
Isn't it like when you like kind of stop the airflow and then you release it all at once like a burst?
Yeah, you have a complete closure and then a sudden release. So you can see that on both the waveform and the spectrogram here. So you see this sudden transition between nothing and something. So this part for here is going to be the closure. But you can't tell when it begins exactly because doesn't make a lot of sound when you make a closure, but you can tell that it's continuing up until here. So that's the closure. And you can see the same thing on the waveform here, right? So that's it's like nothing, 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 and then suddenly sound pressure. So you can see this other kind of phase. It goes up until here. And this phase can be very short or very long, depending on the particular plosive. This is an aspirated plosive. That's what this H means. So if you didn't have your masks on, then I would ask you to say, and you'll note that there's a puff of air that comes out with it that isn't there if you were to say, God. So if you contrast like the English K with French K sound, or Spanish K, like the C sound in Spanish, the English sound is aspirated. It has this puff of air. And what that basically means acoustically is that you have a long period like this kind of extended release. And what you notice is you look at this portion of the waveform. Is this a pretty wave? Nice regular wave? A wave you want to take home and introduce to your parents? No, it's what is called an aperiodic noise. So it's just going all over the place. And so on the spectrogram here, it looks kind of just sort of random. I mean, there are places that are darker and that are lighter, but there's not a regular pattern, right? It's just a mess. And that's aperiodic noise. There's no regular cycle. And so a plosive, a release of a plosive is characterized by aperiodic noise. For an aspirated plosive, that's longer. For an unaspirated or voiced plosive, that's shorter. Okay, and then you get to this point. What happens after that?
Could I ask a question?
Yes.
I know I'm looking at the screen kind of obliquely.
Uh-huh.
It does look to me that the formants are in the noise. So I see a little bit of it.
That's exactly right. So it's your vocal tract does start having resonances when your vocal folds start vibrating. They're there all along. So in this noise, the resonances are going to favor some frequency over others. They're just not going to be as nice and distinct when you're producing a vowel. Yes.
Will they typically be the same resonances as the vowel that follows?
Yeah. Yeah. Or to a first approximation, the difference is while you're making that, while you're opening up that closure, your articulators are still not in the same position as when you're making the vowel. So there'll often be a kind of transition, and that transition will start, will sometimes continue into the vowel a little bit. So I saw this last Wednesday when we're looking at a syllable, sequence of a consonant and vowel. In that case, it started with a P, labial sound, and there was what is called co-articulation between that labial sound and the vowel. You can have co-articulation across that kind of release burst that you see here. Technically, the release burst is right here, but in an aspirated plosive, then it kind of extends on. And yeah. So after that, what do we see in this area? What kind of sound is that? Well, actually, two sounds. It's periodic, yes. It's a periodic. So the waveform is periodic. You know it's periodic because there are nice, evenly spaced peaks. And likewise on the for the spectrogram, there are these little striations that you can see, like there, and there, that are evenly spaced. And those correspond to these peaks on the peaks on the waveform. So any questions about that? Does this make sense? You feel like, oh yes.
So this example is just of a process in isolation,
Right.
But when it's at the middle of a word or at the end,
Uh-huh.
it's really stopping and using after some like the gap. Is it the same as it would be if you're
No, it's not actually. And this varies language to language and even according to style of speech that you're engaging in. So for me, most of the time when I would produce at the end of a word or at the end of a sentence, then it would not be released. It would not have a release at all. So you could only detect the K acoustically by looking at the formant transitions and so the changes in the formant leading up to it, and then seeing the sharp cutoff from the closure. So it's different when you're looking at something. Here we're looking at a simple case where it's the beginning of a syllable, beginning of right before a vowel, beginning of a word. When they come in the middle of words or at the ends of words, it is much more complicated. And so yeah, that's an excellent question. Excellent observation, I should say. Now let's talk about voice onset time. So we've seen one plosive. It was an aspirated plosive, but there are different kinds of plosives. In English, we have a difference between aspirated plosives, unaspirated plosives, and voiced plosives. You might think, oh, three kinds of differences, at the same place of articulation. So this would be the difference between the T in top, the T in stop, and the D in dop, if that's a word. So that seems, there are three different things. But let's say you speak a language from South Asia, particularly one of the Indo-Aryan languages descended from Sanskrit. So many, though not all of these languages actually have a four-way distinction. So, it gets even more complicated than this. But how are these sounds, how are ada, atta, and atta different from each other? Well, the difference is in a parameter we call voice onset time. And voice onset time is basically the time between the release. So it's the time between the release and the onset of voice. So we talked before about the release. This is when you open up like a plosive, an affricate. When you open up the closure, and that's the release. then the onset of voicing is when the vocal folds start to vibrate. And sometimes then this is not so much the case in English, because English Ds, these voiced sounds, or sounds that we call D, like B and D and G, are actually not very voiced in English. It's sort of, we write them that way, and we sort of pretend they're voiced. They're actually not very good examples of voiced plosives. But if you look at a real voiced plosive, like in this ada example, infuriating. Don't know who would actually use that feature. So here, is the release, of course, and the closure is this phase. And if you look down here, or here on the waveform, what do you see? What?
There's little noise.
The sound, is it periodic or aperiodic, do you think?
It's not, you know,
It actually is periodic. It's sort of hard to tell because it's very faint. So this is actually the vocal folds vibrating. So in ada, then the vocal folds are vibrating clear through the closure. So ada, the D in ada has negative voice onset time because voicing starts clear here and the release starts here. So this is negative. If I say atta, then this closure is completely silent. And just right here at the release, voicing starts. And this one, there's maybe a little, you can maybe see a little tiny bit of voicing before the release, but basically the voicing and the release are starting at the same time. So we say this one has 0 voice onset time, or it's voiceless. So this negative one is voiced. This one is voiceless. And then we see the example like the one we saw before, where there's this period, there's a closure and there's a release here. And there's a period of aspiration. And then there is the onset of voicing. So we have positive voice onset. And this we will call aspirate. Questions about this? Yeah. Atta. It would be ada, atta, and atta. Yeah.
Why is it called positive voice onset? Because isn't the aspirate sound like the sound that's highlighted in the third example? Isn't that that's not like a periodic like voiceless, right?
So this release section here, this period of aspiration is not voiced, no voicing there. So voicing begins. Let's try a different color here.
Oh, so the
Oh.
voicing of the vowel that comes afterwards, or the sound that comes afterwards,
Right.
is like ahead of.
So
the closure.
voice comes here. Yeah. So it's talking about this interval between the release and the voicing. And because uh, the voicing happens after the release, then we say that it has positive voice onset time. So this is a tricky thing because a voice onset time is continuous, like the vowel space, right? There's not actually like solid landmarks. The same thing is true with voice onset time. And so different languages have different plosives and so on, you know, at a lot of different points along this continuum. And it's confusing sometimes. So in English, we write David, for example, my name. You know, we write it with a D, and most people would transcribe the first sound as a D. But it's actually, you know, most people don't say David. Who says David? David. David. Who says David? And I assume nobody says David. Just making sure. So you know, a real D, an IPA D would be David. David. We don't say that. So the sound that we make in for the D in English is actually really close to this. So this gets kind of confusing when you look at other writing systems that have been influenced by English. So for example, the pinyin romanization that's used for Chinese, you know, so if you say, if you pronounce this word, who's Chinese or speaks Chinese? Go ahead, can you say that word? Da. Da. So we, in pinyin, we write it with D, right? Let's see. Da. But if we were to put it in IPA, we would actually write it like this. The square brackets, meaning it's a phonetic transcription. It's because of the fact that it's influenced by English and the fact that English D is not really a very good D, then to write a voiceless alveolar stop or dental stop, then in pinyin is a D. So it's all very confusing, and it's all you're like trying to discretize a continuous space. But that's voice onset time. Now let's talk about fricatives. One of my favorite consonant classes. So what is the fricative, just to review? A fricative. Yeah.
It's when you kind of narrow, you force air between the narrow portion.
So what do you think would happen if you forced air through a narrow constriction? Noise. What kind of noise? Aperiodic noise. And that's a fricative is just aperiodic noise. So if you look at different spots in the spectrogram, like here and here and here, you just see this messiness. And that messiness, that's what a fricative looks like. Yes.
What distinguishes the acoustic fricative from like the aspirated period of like an aspirated consonant?
Duration. That's the only thing. You know, the aspirated portion of a consonant essentially is a very short fricative. So these are fricatives. And they're different fricatives. I don't remember what this utterance is. Can't get, I think it got wiped off. So these are three different phrases, different places of articulation. And I can tell you what the one here is. That's an S. Or sorry, I can tell you what the first one is, and that's an S. And you can tell an S on a spectrogram because an S has a high center of gravity. So if you look at where the darkness concentrated, then it's at a relatively high frequency. And this is what distinguishes different fricatives from one another, is where the center of gravity is. So some fricatives have relatively low centers of gravity. So like the th and fa sounds, th and fa. Yeah, so these are relatively low frequency fricatives in the sense that they're the noise, the energy from the noise is relatively low in the spectrogram. Can't really tell this from the waveform, but you can from the spectrogram. So why is this interesting? Well, let's say that you're 5. You're just learning English. Let's say your name is Tamar, and you're my 5-year-old daughter, or one of the two. You might not be able to distinguish very well between tha and fa. Because acoustically, they're very similar. Articulatorily, they're pretty different, right? Fa, you're making by bringing your lip against your teeth. Fa, lower lip, upper teeth, or lower teeth, upper lip. Fa. Fa is made by sticking your tongue out between your teeth a little bit, or putting it right behind your teeth. Fa. Fa, fa. So articulatorily, they're quite different, but acoustically, they're very similar. And so my daughter doesn't say think, she says think, which is adorable, but also illustrative of a general kind of pattern. So has anybody encountered a variety of English where people say fa, where you might say th? Yes. AAVE. So some varieties of Black English or AAVE have fa for th. What other varieties? Has anybody else heard this before?
Heard it on TV.
Who on TV does it?
One of Doctor Who's companions.
Okay. And could you say anything about the background of Doctor Who's companion? Or like where Doctor Who's companion might be from, other than like a different time? I don't know.
Oh, no, he's from the current time. It's the one with blonde hair, in case anyone watches the Doctor before David Tennant. She's a working class London.
Yeah, so working class, there are working class dialects in England specifically that have this property, and it traces back to acoustics and to the fact that the only thing that really distinguishes fricatives from one another is voicing, what your vocal folds are doing while you produce it, and center of gravity. So they get mixed up. It's also true. So in the old days, like bandwidth on phone lines was very limited. So phone companies tried to save bandwidth by sort of clipping the spectrum of those pass through. You had low pass filters to save space essentially on phone lines. But this created a problem because the things that the distinguished S's from other fricatives were high in the spectrum, basically. So it was sometimes very difficult to distinguish like sit and shit, for example. So do you remember these days? I remember this too, being confused, talking on the phone.
Well, I still have that problem because now being a bit older, I'm missing some of those frequencies.
Uh-huh.
So I still have trouble missing the very high frequency things that distinguish S from F.
Mm-hmm. Yeah, I'm missing the middle frequencies. So this this pair of waveforms and spectrograms illustrates another interesting acoustic thing that has to do with nasals and laterals. So you might not think nasals and laterals, like N and L, have a lot in common. And they articulatorily, they don't really have that much in common. But acoustically, they actually have something in common. So does anybody know what this is? What is common about an N and an L acoustically? Yes.
Is it their voice?
Well, they are both voiced typically, although there are voiceless N's and voiceless L's in languages that I speak. So it's not necessarily the case that they're voiced. So they're voiced in English. It's true, and you can see somehow got this totally misaligned. So the N begins here and ends here, and the L begins here and ends roughly here. Yeah, there's like this sudden change in the formants. In fact, there's something that we call antiformants. So they're like these sudden low energy troughs that show up that sort of wipe out the formants. So why would they have that? Well, both of these sounds are produced with a branched resonator. So instead of just having the skull tube, like in our full models, when you make a nasal stop, then you open up your nose, you open your velopharyngeal port, if you'll remember from the anatomy. And so you've actually got two branches coming out of the tube. Well, this means that one of those branches is sort of absorbing sound at certain frequencies that the other branch might like. It might be resonances with the other branch. So you have this sort of, you can think of it as a kind of interference. So there are certain anti-resonances that are dampening energy at certain frequencies. And you might, so that's easy enough to see with nasal, right? I hope. So, you open up your nose in the back, and then you have a branch coming out your nose, branch coming out your mouth, branched resonator. What about an L? Yeah.
You open up two sides of your tongue.
Uh-huh.
Which
Right. Well, some people open up both sides and some people open up one side. But you essentially have a little pocket behind your tongue that's acting as another resonator. So laterals also have antiformants. So they otherwise, so they look a lot the same. And in fact, perceptually, laterals and nasals are quite similar in some respects. In fact, is anyone here from Sichuan? Or know anybody from Sichuan? So have you ever seen, like heard somebody from Sichuan talk? So how would a person from Sichuan say, 老师, 老师? Yeah, there's no difference between N and L in that kind of Southwest Mandarin. So it's because they're acoustically very similar. You could kind of see that as you're looking at this spectrogram. These are the acoustic signal is very much the same.
I have another example of that sound change. Lemon in English is from Sanskrit, like limbu, which in Hindi became nimbu. So there's like an L to N sound change in certain circumstances in like proper thing. Old English.
It's actually exceptionally common.
Yeah.
This is a very common kind of change. So, and it's acoustically based. But one thing you should remember is that L's and N's are pretty similar on a spectrogram and on a waveform. So you should be careful, and that both of them have these antiformants, and so they have a lot of energy compared to other consonants. So, you know, if you look at the waveform, there's a lot of periodic energy there, but they have these sudden transitions where formants get dampened. In other words, antiformants. So R's are also very fun and very distinctive. So the American English R is actually a very strange sound that's not common in the world's languages. There are actually two ways to make it too. Did anyone know this? Two ways of making American English R. So everybody say ara, ara, and pay attention to what your tongue is doing. Ara. Does anybody here curl the tip of their tongue back? Ara. So 1, 2, 3, 4. So you are making a retroflex R. That's one great way of making an R. It's what this symbol actually means. So you're making that sound, ara, ara. And this is actually similar to a sound in Mandarin Chinese, except that it has a somewhat closer closure. So there's a little bit of frication. So if you were to say, trying to think of a good word, a word that begins with our sound in Chinese. Person. I'm sorry, my Chinese handwriting is terrible. Would somebody say this word for person? So it's a similar sound, but it's got a little frication because it has a tighter closure. Anyway, so some people make American English R this way, the retroflex way. Who here makes their tongue into kind of a bunch and moves by their tongue up towards the top of their mouth? Ara, ara. So that's called bunched R. It's usually indicated this way. The fact is, acoustically, these are basically indistinguishable. So two rather different articulations, one kind of acoustics. That's a theme. So how do you recognize these sounds? What do they look like acoustically? Well, here are three examples between different vowels of American English R, which, I mean, acoustically actually also quite similar to Chinese R. So what do you notice about these spectrograms? Yeah, so you see here's F2 and F3, and they're dipping down. And the same thing's happening here. You can only really see F2, there's F3 up there. And here is, similarly a dip down. So if you ask F2 and F3 about R, what are they going to tell you? They're going to say R depresses. Because it's true, it depresses them. And so this is very distinctive. So when I make you read spectrograms on the midterm, which I'm going to do, but don't worry, I'll provide lots of scaffolding. You'll just have to match a word to a spectrogram. But one clue is to look for these dips like this. And that's a sure sign of an R. So here is a mystery spectrogram. And I want you to work with me to figure out what this spectrogram said. Not because I think that spectrogram reading a job skill for you, but because it tells you, it helps you know something about speech acoustics, and helps you to understand some of the issues that are involved in speech acoustics. So what can we say about the first sound? The first sound is a vowel. Look at the waveform. Jeremiah, were you going to say something?
Yeah.
Oh, who said it? I have rather bad hearing, actually. But Lori's hearing is bad in the top range, and mine is bad right in the middle. So, right, like the important part is like missing. So sometimes I don't. Who?
I think I said it, but go ahead.
Oh,
I was just saying, it looks like a plosive.
okay. So it looks like a plosive. What tells you plosive?
Well, there's that like delay in the time
Uh-huh.
the sound gets made. And it looks like it's, well, it looks maybe like it's a little bit periodic, but it's kind of noisy too.
I would say it's aperiodic. Like if you look at this,
Definitely not as periodic as the stuff at the end, for sure.
right.
But I think it's a combination of the late time release
Uh-huh.
and the noisiness.
Right. So it's noisy. This part is noisy, and there's no voicing until we get here. And what about at the very beginning of this noise?
Very high.
What comes before? Nothing. It's void. Formless and void. Anyway. No, there's nothing. It's just blank. And then suddenly there's something. So what kind of sound has that characteristic? What would that correspond to? Articulation? So it would be yeah. So it's an aspirate plosive, right? You have a closure. So a closure here, and then you have release, aspiration, and then voice on time clear over here. Voice onset, rather. So what are the aspirated plosives we could have in English? So these are sounds like and t and k. So basically we got three of them. This is the part where where you look at your IPA chart and also maybe look at a chart that has consonants and vowels for English. But so this has got to be either K, aspirated K, aspirated T, or aspirated P. And so what comes next? So there's something very short after that. And it's a little bit hard to make out. Let's move on for the time being to here, to this thing. What could that be? Is it voice? Yeah, it's voice, because you look down here, and you see that there's a dark bar down there. That's F0. Or H1. Anyway, so it's F0. So is it voice? Is it a vowel? Yeah. It could be a nasal. Why would you think it's a nasal?
There's not really clear formants and it's kind of like sure that it's like an interruption between like two vowels or something.
Yeah, there's like a sudden change in the formants, and there's some dampening, it looks like. So they're antiformants. So it could be a nasal or it could be lateral. And why do we think it's a nasal? So are the transitions abrupt or gradual? Abrupt. So that makes sense if you're making a complete closure and opening it up. So this is probably a nasal. So what are the nasals in English? Well, there's angma, which only occurs at the ends of words. So this is this is this is What?
Does the word say dying?
I can't hear you.
Is the word dying?
No,
Or is the P and an N there?
oh, time. Yeah. No, it's a different word. Here's yeah.
If it's N or M, does N have higher frequencies than M? And so like we would expect that M would basically just have 8 or F1. And
So-
N might have like F1 plus some noise on top of it.
So you for M, then you expect all of the formants to have tip around it. For N, you expect F2 to be somewhat elevated. And for angma, you expect F2 and F3 to come together in the dreaded velar pinch. So you can tell based on the formants of the surrounding vowels to some extent what is involved, but it's tricky. You can actually tell here to some extent, but it's easier. Well, this is a time, you might not think so, but this is a time to introduce the noisy channel model. So who here is familiar with the noisy channel model? So can you tell me about the noisy channel model? What
I remember it being a blender.
is a blender? So yes, the noisy channel model is a blender. Now, So this is based on Bayes' rule, right? So you're trying to figure out, basically in the noisy channel model, you're trying to figure out the most likely, you're trying to maximize the likeliness of one thing based on the likelihood of another thing. An input, let's see, I always get this wrong when I'm talking too fast. Well, instead of getting it wrong, I'm just going to tell you there are basically two terms or components that matter in finding the best result for when you're employing the noisy channel model. And one of these is the source model, and that's just the probability of A. And one of those is the channel model, and that's the probability of B given A. So when you're reading a spectrogram like this, you're employing both a channel model and a source model. And when we're doing like speech technologies, we usually refer to the source model as language model. It's the probability of particular sequence, or rather of a particular, in this case, phoneme occurring given the presence of other phonemes. So it's basically it encodes for us, in this case, our knowledge about what phonemes are likely to follow what other phonemes, and essentially what is likely to be a word, what sequences of phonemes likely to form a plausible word. So that probability is the language model. And then you're doing something else, though. You're not just thinking, oh, this is and it's a very probable word. This must be. You're doing something else, right? What else are you doing? You're looking at the spectrogram, right? You're employing a channel model. A model that tells you about the probability of the relationship between the sort of source symbols and the spectrogram that is encoding those symbols. So so you've set this transcription through the blender, and you've got a spectrogram at the other end. And so the model that tells you about the relationship between the transcription and the spectrogram is a channel model, or when we're doing speech technologies, we call this the acoustic model. Right. So when you're reading a spectrogram, you have a language model and you have an acoustic model, and you're using both your language model and your acoustic model to read the spectrogram, and that's key. So, so does anyone see anything else here that they recognize? Does anybody see another nasal? There are actually two more nasals. Yes.
Like directly above the S in like time.
Right here.
Yeah.
Okay. So that's another nasal. And there's a third nasal. Yes.
Sort of like a nasal into explosive between there and the previous one. I do see a plosive before
that. there is a plosive. Yeah, you're saying like right here, right?
Yeah, that looks like a plosive.
Yeah, that's a plosive. Is it voiced or voiceless?
It's voice.
It's voice. You can see voicing bar here. You can see F0 there. So this is going to be G, D, or B. Anybody else think they recognize? Okay, so this nasal, it's got to be AMA, N, or M. Basically, it's got to be N or M. So I'm going to help you, and I'm going to say there's another nasal right here. Does anybody have any guesses about what the word is? Let's look at some vowels. Let's look at this vowel right here. And also at this vowel. So they're quite similar, but they're different in a significant way. So does anybody remember, so what formants do you see there? I'll draw them for you. So you got three formants. There's a little bit of movement. Is this a relatively high vowel or a relatively low vowel? And how would we tell? What is the rule that we learned? What formant tells you about vowel? F1, right? So if F1 is high, then a vowel is low. Do you think F1 is high here? It's not really high. Oh, you know what? As I look at this, I put F0 F1. So it's actually not really high and not really low. So if it's not really high, not really low, then it must be a sort of mid vowel, right? Is it front or back? Which formant tells you about front back dimension? F2, and if F2 is high, then a vowel is front. Okay, so this is sort of a mid-frontish vowel. So anybody heard of the IPA vowel chart? So if we were to look at the IPA vowel chart, what vowels could be, in this this area? Yeah. So like the S sound. That's epsilon. Then let's look at this other vowel, the one right here. So how is it different? It's kind of hard, like right at the bottom, to make everything out. But how is it different? Is F1 high or low? So it's actually a little bit lower. It's down here. It's almost merged with F0. And then F2 is way up here. It's very close to F3. So how is this vowel different from this E vowel that we saw before? Did you have?
I had a guess.
Oh, you have a guess? Okay, hold it. Let's get the let's get this vowel and then.
Is it more back?
So if F1 is lower or is lower, then this vowel is higher. So what is higher than F? What are your options? So probably maybe E, this vowel, right, with the I. So who can guess? Any guesses about what this word is or this phrase, multi-word expression? Carnegie Mellon. Carnegie Mellon. And that is reading a spectrogram. So you can do it. So on the midterm, I always do this exercise, which I find very fun, and probably students find it tedious. But but I give you 4 spectrograms on theme, right? And 4 words or phrases. And you have to match up the words or phrases with the spectrogram and say why you matched them the way that you did. And maybe provide an alignment between the two. It's hard, but actually everybody does pretty well on that because I tell people in advance they're going to do that and they study really hard and they develop this skill. And I hope it's correlated with understanding. So let's talk about phonetics and speech
Can I ask a question about that? Can you go over where the R's and L's are?
Yeah. So the R, I skipped that because it's kind of hard to see in the spectrogram. But there's an R right here. And then when you get to the N, F2 shoots back up because of co-articulation with N, because that's what alveolars that are not R's do. That's what one R is. And R's look just like vowels on waveforms, pretty much. So they're a little hard to detect unless you can see the dip. And then
the is real short.
Yeah, the is real short. Carnegie Mellon is what I said. Carnegie Mellon. And then there's L right here. And there's a little schwa right here. But it's really hard to see the L. So you have to use your language model. Your acoustic model is just going to do it. Any other questions about the spectrogram? Okay. What time were we supposed to be done? 45. Okay, we'll just get through this. So a long time ago, then people who did speech synthesis and speech recognition a lot about phonetics and phonology, but especially phonetics. And sometimes they even tried to model things directly using phonetic knowledge. So try to model the acoustics of the vocal tract in order to synthesize speech, or model speech acoustics in order to recognize speech. this did not work as well as data-oriented approaches to speech. So what happened, I mean, so ASR was actually the first area of language technologies where statistical approaches came to dominate, because it just worked so much better. And everybody was struggling with all of these linguistically inspired models, and it was just hard, and they couldn't get it quite to work, and it was brittle. And then the statistical models came along, and suddenly we had working speech technologies. And so people have used less phonetics, not no phonetics, but they've used less phonetics in speech technologies. And as a result of this, speech researchers have sort of forgotten a lot of what they once knew about phonetics. So if you look at an older speech textbook, even from the first decade of this millennium, there's a lot of phonetics in it, a big introductory chapter on phonetics. Now you'll get, in a speech textbook today, you'll get much less, some version of the auditory system, auditory phonetics, and some basic stuff, but much less. And somehow, despite not knowing much in the way of phonetics, modern speech researchers still function. So the question is, do they need to know this? Well, there are some areas where some aspects of auditory phonetics and acoustic phonetics still have stuck around to some degree. So is anybody here familiar with MFCCs? What is an MFCC?
It goes a lot of steps.
Yes, it does. Yeah. Yeah, it's sort of a representation of a slice, a time slice of an acoustic signal in terms of series of coefficients. So it's basically a way of representing part of it, one slice of like a spectrogram, but in a because it's scale according to MELs, which are a psychoacoustic unit of pitch, then it incorporates aspects of auditory phonetics. So in this, there's this finding about what the frequency response characteristics of humans are, and it uses an approximation of this curve in mapping, in representing the spectrum. So here is the MEL scale, and more, I mean, speech people for a long time have used MFCCs, and they still do, although increasingly with end-to-end neural models for speech, and they just feed them spectrograms, and the model figures out all of the psychoacoustically relevant stuff by itself, and we have robust speech recognition, and everybody is happy. But does that mean that AI researchers and developers shouldn't bother to learn about phonetics? Well, there are a number of reasons that speech technologies can still benefit from phonetic knowledge. And one of these is in analyzing systematic errors. For example, if you have a model and it's confusing similar sounds in recognition, or in confusing sounds in particular contexts, or if you have in synthesis unnatural combinations of sounds in synthesis, then diagnosing these problems and trying to figure out what can be changed in like the training data in terms of the balance of different things, or diversity, or data augmentation. You know, these are things that somebody with a knowledge of phonetics, even if they're not a phonetician, but who has this kind of knowledge, is capable of doing, that can contribute to these kinds of problems, to solving them, to improving these kinds of systems, and so on. So there are also areas where it's useful to enrich or pre-process training data with phonetic knowledge. So one example of this is grapheme to phoneme transduction, where you take orthographic transcriptions, and you convert it into phonetic transcriptions, or phonemic transcriptions. And also in terms of data annotation protocols. So when you're trying to decide how to annotate data, then knowing some phonetics, if you're doing speech data, whether it's for NLP type speech technologies or robotics, or whether you're trying to represent, you're doing animations of what people are doing when they produce speech, which one of the students from this course last time is doing, then knowing something about phonetics can help you to solve these problems. So it's good knowledge to have. It's good to have this kind of background. Anyway, we're over time. Thank you very much. Good luck with your homework. Let me know if you have any questions, and I will try to answer them. You can go to Canvas to submit the homework, and here.